Yeah. Okay, good morning everyone. Thank you for coming. Today we're going to talk about math in the Waldorf school, a picture of how we develop it over the course of these grades. I can't speak too much about what happens in the early childhood village because there's nothing specifically that happens in the early childhood village for math, other than the most important thing of all, which is the foundation developmentally by letting them play. I'll say that so many times no matter what subject we talk about. Letting the child play freely is so important for developing their bodies, their coordination, their basic skills. And of course that has its neurological corollary, which enables them to do all the different skills that we're going to teach them, including math. So we're going to look at how we progressively approach math through the grades. So when the child comes to us in first grade, the first thing we're going to start doing with them is helping them transition from kindergarten into the grades, from kindergarten, lots of play, meaningful play, into play that's a little more structured, a little more leading toward lessons. So we could have them do something, for example, like this. I might tell them a story about a beautiful forest with a cool, shady, mossy fen where frogs and toads live together. They could go on a whole adventure together, just so that these children live with a warmed imagination of frogs and toads. And then when we come to a math lesson, I could say, on this particular day, around this little pond, there were 9 frogs and toads. And I could have them hop like frogs and toads. I could have them stand in groups of 9 to experience being a group of 9 frogs and toads. We could count off each other. If we had 9 people here this morning, I would have us do all these things, but we don't. These are the things I could do with children, however. I might teach them a song about frogs and toads. I know one. Oh gosh, I knew one. Maybe I should say. Kaeru no uta ga kikoere kuru ro. Gwa, 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 gwa. Gero, 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 gwa, gwa, gwa. That's a Japanese song about frogs that was taught to me in my teacher training year by our Japanese students. And that was a miracle that just came back. But we could do all sorts of things. In other words, getting them to move and to feel some connection to all this idea of the imagination of frogs and toads. So that this math lesson that I'm going to bring to them, it lives in a context, a wholeness that they can experience on every level. This wholeness is a real principle we work with in all of our lessons, especially emphasized in the lower grades. We want to move their experiences and their lessons and whatever it is they're going to do in the different activities from whole to parts. This is a very important principle that we use over and over, moving from whole to parts. So in this case, I'm building for them a whole experience. They're coming out of their whole bodily and imaginative experiences to approach a simple lesson like this, where we have the 9 frogs and toads around the pond. And then I may give them little glass beads, sometimes called dragon tears, to put on their desks, rather than marbles, which would just roll away. But something that they might now move. They've already done all this movement with their whole selves, and now we move toward parts, and they move these little things on their desks. For example, I might have 9 frogs and toads here on my desk. And I ask the children to determine for themselves, you can create however many toads there were and however many frogs. And I have, as the teacher, used 9 so that it's not going to be an even half and half. I've chosen an odd number on purpose. So, doesn't mean you can't use an even number, but I'm using an odd number today because I want them to see that it doesn't need to be half and half. So they could do any combination. They might say 1 toad and 8 frogs. The other child could have said 3 toads and 6 frogs. On and on. Every possible combination could be out there on their desks. So again, it's another picture of how we've moved from doing things as a whole class together to doing things a little more individually. No matter what it is they do, I ask them to tell me, and I might write them on the board. Oh, there are 3. So if there are 3 toads and 6 frogs, I could write 3 plus 6. I've moved from 9. I started with the whole, and we've broken it down into parts. 3 plus 6. Pretty simple concept. But when I do all these things, at first it's going to be a little bit random because that's what they are going to do out of their own imaginations. Now we're moving. Then, when I present it on the board and have them actually create a lesson or a page in their main lesson books, I'll say, okay, there were 9 toads and frogs. Now I want to create a little more order as we're going to create our lesson pages. So we'll take one of those combinations was 1 toad and 8 frogs. Another combination we heard, may get written randomly elsewhere, but here we're creating our lesson page. 2 toads, 7 frogs. And of course, this goes on and on. And you're seeing, I hope, what I'm doing. I've created a little more order for them to see and experience than they would have created out of themselves. It's okay that they created a little bit of randomness in their activity, because to them it was very meaningful just to work on their one desk about their division of 9 into 2 parts. But here, when we rearrange it, I want them to see an order. 1 plus 8, 2 plus 7, 3 plus 6, and on until eventually we have 1 through 8 over here and 8 through 1 over here. It's a first simple but very important lesson about math having order. Something that we may not have experienced if our math teaching, the teaching we experienced in math, was worksheets. If we received those random ordered worksheets that we were just supposed to do, and maybe even in a certain limit of time, we may not have had the ability to see the order. Now, by limit of time, I was saying, you get a worksheet, here are your addition problems. Do as many as you can in 60 seconds, which is a pretty common exercise in school.
Not in this school.
Not in this school at first.
Oh.
We do it later on, but only after they've seen the order, seen the beauty. So there's a certain wholeness here too that we return to. So we go from whole maybe into a little bit of a broken up parts type experience and bring it back to a wholeness so that they can see, wow, there's beauty in this, there's order, there's a harmony even in math, which for so many people seems like a cold subject, something that people have phobias about math. People identify themselves in relation to math. I'm not a math student. I'm not good at math, etc., which is unfortunate. So beyond this simple lesson, we can also do things, like I said, out of their whole experiences. And we don't want to, just because we've begun writing things on paper and on the board, we don't want to go away from this foundation of movement. So there are other things we do to keep math alive in their whole bodies. And again, it has a little bit of an imagination, but it's also based on their movement experience. So I could give them a verse, for example. I walk with you in my new shoes. 1, 2, 3, 4. 5, 6, 7, 8, 9, 10, and so on. And I can change that verse very easily. We could do that verse for weeks and weeks. With the young child, they don't tire of this. The whole idea that we're stamping loudly on one beat is fun. That's joy. So we do it a long time. And they have no idea that this counting along with it is actually enforcing a patterned understanding of math. That's good that they don't know that. I would never say that to a first grader or a second grader. I wouldn't say it to a third grader or fourth grader or fifth grader, probably. But then I can change the verse very simply into, now, I hop with you in my new shoes. 2, 4, 6. A very simple transition that if they've established the pattern over those weeks of knowing that that 2, 4 came on that second beat, and now we're doing 2 feet together, it's a very simple transition. Same with moving into 3s. I wrote these verses this morning, so I don't have these memorized. I am old, gray and slow. On my cane I must go. Could you hand me one of those canes there? Thank you. I am old, gray and slow. On my cane I must go. 1, 2, 3, 4, 5, 6, 7, 9, and so on. That may seem sad. It will speak to the melancholic hearts in the class. But we can also bring playfulness to even such an image. I am old, gray and slow. On my cane I must go. 3, 6, 9. Same concept of transitioning from the individual counting with an emphasis to the skip counting, which is so needy for the child to do if they are going to ever learn multiplication tables. Seeing the patterns of division, being able to move that into fractions later on. Seeing and experiencing patterns is the first most fundamental key in approaching math and numbers. And if we can bring them to those experiences through these playful little imaginations, stories about anything. I told a story about a baby elephant that we named Babyphant. For years, Babyphant taught us math by going out in the jungle and having experiences. So it's this experience, imaginative approach to number that prepares them for more sophistication later. There are these individual activities that we do both as a whole class, and they're having their own individual experience. And there are also activities we can use for learning with our classmates. And now I would bring this type of activity after the 9-year change, which usually happens in 3rd grade. So we're talking about a late 3rd would be really advanced for some students. I would bring this probably in 4th and 5th grades. And you see here, all I have is a rope with knots. So I didn't measure it out perfectly. That's really not that important yet. We don't need to know that this is a particular length, even if it's a little bigger than this one, let's say. But we just have these units, these points on the rope, and we can count them. So we're going to use them to do a particular exercise. Could I have your help? Sure. Can I have your help?
Sure.
Eventually we're going to hold this up so everybody can see it. But what we want to do is create a rectangle. We would need one more volunteer, would you? We're going to create a rectangle. We'll hold this up too. He'll need to take me in now. And this rectangle will be 12 square units. Now let's remember how these square units work. Excuse me. If I were to make rectangle that was 8 square units. It would be like this. 1, 2, 3, 4, 5, 6, 7, 8. And we see that there are 1, 2, 3, 4. 1, 2. 1, 2, 3, 4. And 1, 2 units along the sides, right? So this is 4 by 2. Does that make sense to everyone? So if I wanted to make something that was 12, let's see how that would work. We have to do this without talking to each other. Melanie's not going to move. She's the lucky one. She has an end, but you might have to adjust. And you all are going to wait to see what I do, to see what you might have to do. Yeah, and then just pull it tight so that, there we go. I may have confused you with counting the knots. It's more about counting the sections. Right? 1, 2, 3. 1, 2, 3, 4. Yeah. And then would you take that knot so you hold it so you got a corner? And now, yeah, and you can let go of that one. She'll hold that one. You can let go of the end. Yeah. And then we'll raise ours just to show it to everyone. There it is. Again, not a perfect measurement because some of these sections are longer than the others, but we have something that is...
We need one more section.
You're right. There we go. There, now we have it. And you can really see how the sections aren't the same. So it's not a perfect rectangle, but we have something that is 1, 2, 3 sections by 1, 2, 3, 4 sections. And a couple of things were happening there as we whispered a little bit to each other, but in working on this as a group, go ahead and keep holding that. Working on this as a group, we might have to adjust. What if I changed my mind as we were working and you're all adjusting to me because I'm in that first position and I said, maybe I was confused, but I adjusted and I moved to this. Now suddenly I've changed it to 4 sections on this side. You all would be adjusting. Exactly. So there's a real, not only rigidness in terms of mathematical truth, there's also this social flexibility that we have to incorporate when we're following along with somebody else. So there's this individual experience and there's this group experience. And what if Thad is sitting there the whole time knowing when I do this and we're trying to make 12, he knows that this is impossible. I've created a section of 5. There's nothing evenly that will create a rectangle of 12. What's he going to do? His options are to begin pitching a fit and telling me that I'm wrong. But if as the teacher I've really cultivated a healthy, harmonious working where we're being flexible, he will give me time. He'll just wait. And I might have, when I see all my friends just waiting, I might have to rethink what I've done here. And I have an aha moment perhaps. 30 seconds later, maybe even a minute later. But what a gift it would be socially in class if I realize, oh, it's 4 or it's 3. It's not 5. For me, it's a real gift that you all would have given me that time and space to learn, truly learn. And for you, it would be a gift to just have that practice of allowing another time and space even when they are wrong. What a different world we start to create with little things like that in a math lesson, right? Okay, thank you.
So I have a question about that.
Yeah.
Would you say that the purpose then of them having to do it without speaking is to create that scenario where they're not criticizing each other when there's mistakes made?
That's definitely a huge component of it. And the other is just to provide each other the space and to prevent that one choleric child. I keep referring to these temperaments, but the choleric children, of course, are so tempted to take charge. Instead of allowing the group and every individual to have his or her process, they start saying, 3, just move to 3. And now the sanguine child, who maybe gets along well with this choleric child, says, oh, yeah, I'll move to 3. So she gets to the right place, but she didn't have to think about it at all. She just followed a direction. There are times to follow directions, but in this activity, we want everyone to be actively engaged. So that's a big reason, too, not to have them speaking, because those cholerics will start to take the thinking and processing piece away from the other children. But definitely there's that social component that hopefully, if they build in such a little math lesson, radiates out into all their other activities, even on the playground. If they have this experience of, sometimes I don't have to correct my classmates. In fact, I'm growing accustomed to allowing them some time and space to process what it is they may think they're very right about in this moment. Like a rule for playing a kickball game. You may be convinced about this thing you're upset about right now. And I may have a conversation with you about it, or I may say, why don't you think about that for a minute? What a different approach we could begin to create with people socially when we start to allow for that time and space. I'm not saying it always happens that way on the playground, but we give them these seed experiences that hopefully we can continue to grow. And this is, again, in a math lesson. So, again, I wish we had more people. I would show you another similar activity where we just say, I think you can all imagine this. Instead of using the rope with knots, we just use ourselves, our bodies. And I call up maybe 12 students. And I say, again, we're going to do this activity without speaking. All you get to do is move your own body in space. You're not going to point, tug, nudge, do anything where you may even feel that you're just helping your friend who's struggling. Just allow them the space and time to do this activity. So here we are, we're 12 people, again, starting with the whole, and we need to make 3 equal groups. Go. And they start to move themselves. Now, of course, all sorts of things begin to happen. Janet wants to be with her best friend, Susie. Maybe Kellen doesn't want to be in the group with Danny. You got all sorts of things at work there. But regardless, all I'm going to say as the teacher, if I have cultivated a good quiet mood around this where they really are following the directions, all I'm going to say occasionally until they find the answer is, we're looking for 4 equal groups. Did I say 3 the first time? 3 equal groups. Of course, we can switch that later. But 3 equal groups. That's all I'm going to say. And if they get into groups of 5 and 7, I'm just going to watch them for a while. And if I think they need a reminder, I might say, we're looking for 3 equal groups. However long that may take, they will find it. They will. Yes?
Is this first grade?
Oh, no. This could be in any grade. Certainly groupings like that in terms of what we're basically doing is division in movement. I would probably start bringing that at the simplest level in 3rd grade. 3rd, 4th, and 5th, they like it. Start doing this in 6th, 7th, and 8th. They don't like it as much unless it's just a novel looking back. Remember when we used to do this? Oh, yeah, that was fun. And of course then, once they find that those 3 equal groups are groups of 4, then I do the obvious. I say, okay, now we want 4 equal groups. And they move it to groups of 3. And it becomes a moved, experienced understanding of math groupings, of factoring. I mean, we can call it all sorts of names that don't make nearly as much sense as moving it in space with your own body and seeing this is how it works. And oftentimes I will put myself in the group and play the trickster. So as soon as everybody thinks they have those 4 equal groups, I just change my mind and I move to another group, and they have to adjust, which brings around that flexibility. We can do this with manipulatives, with their bodies, and then of course I can just have them imagine it. Yes?
You know how you use somebody's telephone number all the time, and then you know it so well your hands do it, but your brain, when you try to tell somebody what the phone number is, you don't know it. It's just your hand that knows it.
Oh, wow.
You know that? You know that?
I vaguely remember that experience back from the push button days. Yes. And now all of my phone numbers are just in my contacts.
Sorry.
No, it's good. It's a good reminder of how that used to be.
Mm-hmm. Well, there are other things. That was just one that I know for my. But anyway, so is this in the neurons? Is this the same kind of?
That's a good example of how habits can be so strong when we form them through repetition. And you know, if it's I would think it would be even more likely to happen when I'm calling someone I like. I'm probably going to remember that series of buttons that I push better than if I have to call to pay a bill every day. It's going to happen because there's an association too. And this is a big point about Waldorf education. We can do things through pure repetition. We can make habits form. But far more effectively, we find, is when we do things through repetition and we combine that with a good feeling of harmony and beauty and truth. And so that's why I say, if you're calling a loved one, like if I'm calling my mom's number, and I love my mom, then I'm probably more likely to form that movement habit and not even think about the phone number. I remember my phone number from when I was a child, a number I haven't had for decades. It's locked in. There were good associations with that pattern of both dialing and thinking. I not only remember the push button dialing, I remember what was that called? The round...
Rotary?
Rotary. The rotary dialing. I remember that. Being very impatient about how long it took to swing back. So there's another activity we can do with the children that brings them a beautiful, harmonious experience of maths. And this would come more in 4th grade. So we can have a wholeness. And I can say this is a pie, of course, the pizza, all those examples are easy. And I can use any imagination for it. But what we're going to do with it now is what's even more important. If I have a bag of apples, and I was going to try and divide that bag into parts, now I'm going to divide this wholeness into parts, and I can say, well, I want to divide it in half. That's pretty easy. I can make a line, go through the center, in any direction. That's half. This is half. This is half, and so forth. But that's really simple. I can also bring them a form drawing lesson if I say, this time instead of using a straight line, let's use a curve and still create a half. Now, it may not be mathematically perfect, but they understand the idea. I've done the same thing virtually on both sides of the center point, coming from the outside and going to the outside. And I could do that over and over with different combinations. All sorts of ways to creatively make half. So now with the most simple of mathematical expressions, half as a fraction in 4th grade, I can bring an artistic activity that they start to enjoy. And of course they want to color these in later and do all their things that these Waldorf kids do to make things beautiful, which is great because again, we're reinforcing a warm experience of what is a very cold and abstract concept, this half. And then we can move, of course, to quarters, which is very simple with a straight line, but gets to be even if I was just using straight lines, it could be much more intricate. Fun ways to play with fractions coming from whole to parts. This was brought, I learned this from a man named Ernst Schubert, Waldorf teacher and pedagogue from Europe, and he would refer to this as fractionizing, which is a great experience of moving from whole to parts. And yet, there's still a wholeness that we return to when we bring our artistic activity to it. So it's just another way of approaching math in the Waldorf school. It's not necessarily anything exclusively Waldorf about it, except for how we bring it, how we want to incorporate those feelings of harmony and beauty and creativity along with this abstract concept of a half or a quarter or thirds. Thirds are fun because triangles lend themselves so well to the thirds. Again, I can work with the center point and I can do all sorts of things. As long as I do the same thing over and over, I get thirds. So we're teaching them about a really dynamic bit of geometry as well. That I don't even have to call it geometry. I just say, well, we're going to make thirds. And we're going to do it in a creative way. And I'm engaging their creative will forces by encouraging them to be active creators of their own third fractions. And the children, once they understand the idea and the techniques to do so, so it actually comes out more or less evenly, they get really creative with what they create for it, these fractions. Yeah. So to try and finish up, in the upper grades, of course, here at Live Oak, for example, we have 1st through 8th grade. We know that most of our students are going to go on to public high school systems. Some of our children go on to the Waldorf High School in Sacramento. Most go on to public school. Even if that weren't the case, we would still feel a certain responsibility to give them skill sets that are useful in the world today. I mean, we have a sort of a Waldorf bubble that we live in, of course. We're trying to protect the beauty of childhood and help them experience that as fully as possible. And at the same time, we must recognize that within the context of the greater world. So they're going to be tested. They're going to have some skills in fraction work in 4th grade and working with algebra in the upper grades, working with geometry in the upper grades, understanding basic skill sets. There's no way around building those skill set habits other than repetition of those types of problems. So these creative approaches that we bring are really the introductory steps. Thereafter, we do as much as we can to keep their imaginations engaged. But if you really want to build strong habits for working math problems, eventually you have to break away from the imaginations and the pictures and the movements and the games that we play and get into just working numbers. When we get there, hopefully they've got that foundation of knowing that this more mental aspect that we're getting into is still based on that beautiful order and experience and harmony that we knew from before. And then I can begin to bring them what I call math tricks, because always working on the paper can get tiresome. It's important to do, but you've got to balance it. So I start to bring them math tricks to see that I can even instill confidence in those children who aren't as strong at math. And some of them aren't. That's just how it is. We all have our strengths and we all have our challenges. That's a given. But even for those who aren't as strong, some of these tricks are really fun and easy. So I can show them this. That's an easy problem to do in your head, just like that. You know it? Oh, you were not. I thought you were nodding like, oh yeah, I know this trick. This trick is super easy. You just take the, oh, there's a 4 here already. Take the 2 4s and split them, and then the number in between is their sum. The answer to 11 times 44 is 484. The answer to 11 times 33 is 363. The answer to 11 times 24, anyone?
264.
264. And doesn't that make sense? Because if I work it out in the classic way, I would have 24 plus 24. That's why it works. We just split the 2 numbers. Here they are, and we add the middle. This is how we learn to do it. And maybe I never thought, as a student, as a child, I never thought, oh, that would be easy to do in my head. Until as an adult, somebody said, you know, you can do that in your head really easily. I said, oh, that makes perfect sense. And of course, we can do it with numbers where we have to carry. We just carry. And I know it's going to be 13 in the middle, so the answer is actually 737. Now, I'm taking you through this really quickly. With the class, I can take weeks to develop this. I can start with these simple numbers at first that are very easy to add, no carrying, even the same digits, 44, 33, 55, 22. Actually, 55 carries. 22, 33, and 44. Really simple to bring the concept to them, and they build their confidence. And slowly but surely we branch out until eventually we're carrying. And it becomes a much easier process.
What were you multiplying 67 times up there? Is that?
Times 11.
Oh, okay.
These are all what I would call the 11s trick.
That's the 11s trick.
Yeah, the 11s trick. And of course, they learn other tricks. I mean, 10s, once they see the order, is a trick. It's a little trick. Oh, just put the 0 on the end. That's a trick. What's 5 times 10? It's 50, because you just put a 0 on the end. They're not counting by 10s. 10, 20, 30, 40, 50. They might be in the lower grades, but eventually they learn these little tricks. Oh, you just put the 0 on the end. Oh, that's easy. There are other tricks. I don't want to overwhelm anyone, but I'll teach you a couple more. There's a teens trick. I'll use a different color just for fun. Teens trick. So, what if I wanted to multiply 12 times 13? There's actually a really simple trick to do this. I'm going to take the top number, and just like I was saying about 10s, I'm going to put a 0 on the end. I'll say that's 120. I'm going to take the ones place of the bottom number, and put a 0 on the end. That's 30. And then I'm going to take the two ones place numbers and multiply those together. 2 times 3, 6. When I add all this together, I have 156. And that technique will work every time. All teens. Why though? Why can I just approach this so differently than the traditional way we learned to do it? And this again is building flexibility of thinking for the children, because I can show them why this trick works, even in writing. In writing, we typically learn to move from the ones place toward the larger place values. So from the ones to the tens in this case. So I say, what's the first step? 3 times 2. There it is. Then I say 3 times 1, but this 1 is in the tens place. I'm really saying 3 times 10. There it is. Then I say 1 times 2, which is really saying, in the tens place, 10 times 2. There it is. And here I'm saying 1 times 1, which is really 10 times 10, because these are in the tens column. There it is. We just worked it backward, you could say, doing it mentally. But it gives us, of course, the same answer. They love this trick because, of course, you build in complexity until 19 times 18 becomes a very doable number. 190 plus 80, we're at 270. 8 times 9 is 72, so 170 plus 72, 242. And even with the children who are a little bit challenged by math, doing this slowly over time, and when I say time, I'm talking about years. Here we've been doing this for minutes, so don't feel bad if it's not clicking immediately for you. But I'm talking about months and years. They learn proficiency with this. Maybe 19 times 18 is always going to be challenging for Johnny. But he gets the idea, and he knows that if I just hang in there and if I know my 9 times tables and 9 times 8 is 72, and if I start to see how I can carry that in my mind and hold it all, this is a struggle that is worthy, even if he never gets to where he can click them off quickly. Just by engaging his will forces, even cognitively, he's building a habit life and a mental power that will serve him. We don't always finish running the mile. Sometimes we get a cramp and we tire out. But do we say, well, I shouldn't run at all because I can't finish it? No, it was good to run the 3/4 of the mile that you ran. Same idea with everything. Whenever we engage the will, we want to have them struggle. Not stress, struggle. Okay, one more trick I think you'll like. What color should I use? Maybe the white we haven't used. I think you'll like this one. Splits. So, everyone can know this. 30 squared. This is an easy concept. Squared means a number times itself. So to do this, I can just say 3 is squared. And now I have 2 zeros. So 30 times 30 is 900. That's an easy trick to learn. 3 squared, 2 zeros. Easy. And I can use this to my advantage when I see things like this. (32 times 28). I can do that in my head very, very quickly. It's 896. And that was really easy. Actually easier than this. Because I can recognize the split. These are both 2 away from 30. Okay? Follow that? So I'm just going to say then the answer is 30 squared minus the split, the difference. They're both 2 away from 30. 2 squared. 30 squared minus 2 squared. That's very easy math. We know that 30 squared is easy. That's 900. 900 minus 4. That's 896.
Does that only work if they're the same amount away from 30?
Has to be an even split for this trick to work.
Mm.
Yes. Otherwise, we're into double-digit math, which is another trick I teach them mentally. It's very much harder. You're holding big numbers and working through them, but still doable with lots of practice. We once had an 8th grade assembly where I had 7 students. Literally, we let the audience call out random double-digit numbers, and they beat the people who were holding the calculators.
Right.
That's with practice. That's with practice, really, really quickly. And sometimes the audience would give them tricks, not knowing it. Somebody would say 32, 28, and the kids would sort of, smile at each other like, well, that was easy. Or they would give us a 99, thinking 99 is really hard. 99 is one of the easy ones. 99 times 37. All you need to be able to do is subtract. This is an easy, easy problem. Because it's 3,700 minus 37. Because you don't want 100 37s, you want 99 of them. Here's 100 of them and take one away. Right? It's 3,663. Easy. And when the kids would get, the audience would be like, 99. And the kids would be like, okay. Good. That's one of the easy ones. If only the audience had known to say 98, that would have been the hard one. Yeah. So the last thing I guess I want to end with is how can we bring a subject, so if you go on the whole journey of math through the grades, we're of course introducing these beautiful, simple little patterns of numbers. We're teaching them the 4 processes, and we use, if anyone is familiar with the Waldorf methods, we use these characters to appeal to the different temperaments. You sometimes hear about Prince Plus and Minister Minus and Daddy Divide and so forth, which is great. Those are great things to use. But we use all these imaginations in the early grades to, again, set this nice foundation, this warm feeling connection to the subject, to number, to the beauty of order and pattern. We can give them these tricks. We can bring these artistic activities in the middle grades to keep their imaginations and their sense of beauty alive and connected to math. And still, as I said, we have to build skills. So we know we're going to come to a subject that would be very, very difficult to introduce with a story, like algebra. We do introduce algebra in its most initial stages through business math, where we start to use a variable for the first time. There's now going to be an equation where we've got to discover the value of a variable. And in business math, we teach it not as like how you're going to calculate your interest for your savings account at first. We certainly bring that. But at first we introduce business math with the most simple economic pictures. How 2 islands might trade goods, for example, because one island is rich in this particular product and this island is rich in that. But eventually that's going to develop into a need for currency, because you can't always trade cattle for refrigerators. That's just not practical. And so that's why it develops. But if we really want their algebraic skills to grow strong, we're going to have to get away from the imaginations. We're going to have to bring them into those rote practices. Just do things over and over. And this is why so many people hate algebra. But we can do some other things that appeal to this child who has either begun to experience, is experienced, or is starting to get away from the experience of puberty, where we see the cognitive forces coming to the fore of their activity in class as well. So I can bring an example like this, and I'll start very simply. I'm thinking of a number. If I add 2 to this number, I have 10. What is the number? 8. How did you get that?
I think it's just programmed in my mind. 8 plus 2 is 10, or 10 take away 2 is 8.
Or 10 take away 2 is 8. So
Same,
I
same.
said, I'm thinking of a number. If I add 2 to it, I have 10. And either way you go, you can get there. I think the second way you described it might be the most beneficial for those who were sitting there going, how'd you do that? Not that that was any of you. I'm just saying in a classroom. When you say, I started at the end with the 10, and instead of adding the 2, I'm going to take away the 2, and I arrive at 8. So let's try that. Start where we end. Do the opposite process that I described. I'm thinking of a number. If I add 5 to this number, I have 12. The number is 7. Simple, simple. And so we can begin to complicate things, just one step at a time. I'm thinking of a number. If I double this number, I have 18. Now they see the relationship of processes too, right? Because if you're not doubling, what are you doing? If you're not doubling, you are dividing by 2. We're halving. If we're not doubling, we're halving. You don't have to say halving. Divide by 2 is fine. If we're not multiplying, we're dividing, right? They start to see relationships too. So then I can add multiple steps. I'm not trying to put any of you on the spot, but I could say, I'm thinking of a number. If I double this number and add 1, I have 11. 5. Take away 1, divide by 2. Right? Take 11, take away 1 is 10, divide by 2 is 5. And with the students, again, developing this over time, we see that their ability to hold numbers and work more and more multi-step and more complicated problems becomes easier and easier. They have no idea that this is actually what they're doing. Would you help me turn this chalkboard over? You're going to have to scoot it out. Yeah, it doesn't slide very well. There we go. And then loosen that handle. And then tighten it again. Yeah, great. Yes. Thank you. They have no idea. Because I'm thinking of a number in 4th grade, maybe even 3rd grade. If I just say, I'm thinking of a number and I add 1 to it, that gives me 7. It's really easy. They almost don't even think about going backward. It's 6. So easy. So I just keep it easy. And I just stretch them just a little bit, year after year, till by 8th grade I can do a problem like this. I can say it, I'll say it first. I'm thinking of a number. If I square this number and add 3 to it, the cube root is 3.
you adding?
Yeah, I'm going to say it again. I'm thinking of a number. If I square this number and add 3 to it, the cube root is 3.
What's a cube root?
Oh, good question. Cube root is the number that would be multiplied 3 times to give me that answer, instead of a square root, which is the number multiplied by itself.
Gotcha.
Yeah. I'll say it again. Thinking of a number. If I square this number and add 3, the cube root is 3.
3 or 9?
Let's look.
Is it 9?
I'm thinking of a number. Never did I say in the years leading up to this, I'm thinking of a variable, because we're doing mental algebra, children. Even though we were, from the very beginning, doing mental algebra. We were, even in 5th grade. I'm thinking of a number. If I square this number and add 3, the cube root is 3. Later, they'll learn how to work this problem algebraically in writing, but it is exactly the same process I've taught them over the years to do mentally. Go backward from where we ended, from your answer, move backward and do the inverse process. So instead of the cube root, we're going to need to, I'm going to really write it completely comprehensively. We're going to need to cube our answer. Now, cubing a cube root just cancels all that out. So what we really have is x squared plus 3 equals 9. Now this is still in their heads because they're moving backward. 9, goodness gracious. I'm so sorry. It's 27, the cube root. Cubing 3 is 27. That's why I was getting confused. Now, we have to, remember we're working in reverse, we have to subtract, instead of adding the 3, now we have to subtract the 3. So we wind up with x squared equals, I did not set this up properly. Is that why everybody was lost? I did this completely wrong.
I'm following you. I don't know.
Completely wrong. So sorry. We're not going to include this on the website. Was this being streamed live?
No.
Oh, that's good. Oh my gosh. I kept looking at this thinking, what am I writing this so wrong? Now I realize the whole thing was wrong. Let's start over completely.
Sounds good.
I'm thinking of a number. Oh, wait a minute. We're going to have to erase all this.
While you're erasing, can you say if you relate some of these things to real life, like in a recipe or plotting out a garden, square foot garden or something like that?
Oh, absolutely.
Oh,
Sure. Gosh, if we had more time, I could do a whole lesson on the Pythagorean theorem, which is basically what we would do with that activity that we were doing with the rope. I mean, when you get a group seeing how to create together squares and rectangles, that's really just a factoring exercise, right? You say, I want a rectangle that is 48 square units. That's 6 times 8, right? Or 8 times 6, whatever. But then you can take them to right triangles very easily if you say, I want a right triangle that is 24 squared units. Yeah, sure. 24 square units, because all they have to do is cut that rectangle in half. Does that make sense? Let me show it. Let me show you what I'm talking about. This is a good question. once they learn how to do this really quickly as a group or even on their own paper, it's very easy to introduce the concept that half of a rectangle is a right triangle, and therefore half of this area is this area. So to create the right triangle, it's actually the same dimensions as a 48 rectangle if I want a 24 right triangle. So to make a practical expression of that, I could just say, I'm going to create a garden plot. My house is on the corner of a street, and I'm going to have to make a fence this way. I have this part of my lot is 8 yards, and this part of my lot is 6 yards. How many square yards am I going to have in my garden plot, for example? And they would say, oh, it's 24 square yards. Or I could work it in the reverse. I've got, I want to have at least 24 square yards. How big of a plot am I going to have to be if I'm making a garden plot that's a right triangle? You go a lot of different ways with that. Let me try and dry this off. God, that's so funny. I've done that before with large groups where everybody's staring at me like, what are you talking about? And I realize my own math is off. Okay, try again. I'm thinking of a number. And I'll do the same process, I'll just make it work. What'd I do? Did I square the number?
Cubed.
Oh, cube root, okay, right. I cubed it, right. I'm thinking of a number. No, I squared it first, right? Squared it and took the cube root. Squared, added, took the cube root. Let's do that. That means I'm getting to a cube root. Okay. Well, we'll just change that same one very simply. I'm squaring this number. I'm thinking of a number. If I square it and I add 2, and then take the cube root. I'm thinking of a number. If I square it and add 2, the cube root is 3. There. Now this is easy to work mentally. Instead of the cube root, I'm going to cube this. Are you doing it?
I'm trying.
Okay.
Okay.
Got it? Did you get an answer? Uh-oh.
I hope I did.
I hope I did too.
Okay.
Let's see. Yeah, that works. Okay, so instead of cube rooting this side, I'm going to cube this side, or I'm just going to go backward and say, instead of cube rooting, I'm going to cube this. So 3 cubed, 3 times 3 times 3. 3 times 3 is 9, times 3 is 27. So now I've got this. Instead of adding 2, I'm going to subtract 2. Instead of squaring, I'm going to take the square root. Now that's the simplest written version, where I didn't write all the canceling and doing the same thing on both sides. But I hope you can see how we were working backward mentally. If not, that's okay, because it takes years for the students to get this. But I'm doing the same thing I have to do algebraically, mentally with the children. Just working backward from the answer given using the inverse process. That is how you, as algebraists would put it, isolate the variable and find your answer. Find the value of x. That's how you do it. Exactly the same way we would do it mentally. Now this is very complicated. I could say, I'm thinking of a number. If I add 2 to this number, half of that is 8. I'm thinking of a number. if I add 2 to this number, half of that is 8. Keep going. No, yes, I went too far. Sorry, yes. 14. Yeah. So instead of having, I double. And instead of adding, I subtract. The exact same thing we do in algebra, we can teach them to do with their minds. If their minds have been strengthened all along the way through physical activity, joyful connection to that activity by giving them songs and verses and imaginations, creative processes of those drawings and the fractionizing we did, and then eventually we can set their minds free to just do these kind of mental, purely cognitive exercises. And some of them can really gallop. Some of them are just math whizzes because that's their gift. Some of them always struggle a little bit, but at least they go as far as their potential can carry them. And they're going to do the best they can in the upper grades math or the high school math or even college math if that's their path. Because we've given them the best foundation possible for approaching it. So, the reason we do math the way we do it in the Waldorf school is not to try and get the highest SAT scores. It might be, though, a byproduct of what we do. They might get the highest SAT score that they themselves, that individual child, could possibly get. But far more importantly, they will have a living experience of number and math in their lives. They will see that order and beauty and pattern exist all around them in the natural world, in the plant kingdoms and the animal kingdoms. They will also not have a phobia about doing simple tasks like balancing their checkbook or understanding what this contract means around the interest rate that's going to be applied to their debt. Simple little mathematical functions that we need in our daily lives won't be as intimidating as it might have been. And their experience of their whole lives will hopefully be more harmonious. They will live with a deeper sense of wonder and awe for how math lives in all the world around us. That's it.